Now we'll be looking into vapor power cycles. Vapor power cycles. Now the first is what we call a Carnot cycle. Vapor Carnot cycle. Now the Carnot cycle is the most efficient cycle operating between two specified temperature limits, but it is not a suitable model for power cycles. Not suitable, even though it is the most efficient. Okay, but we still have to know what is the vapor Carnot cycle about. So in vapor power cycles or steam power cycles, we'll be looking at the vapor Carnot cycle first thing. Then we will be looking at Rankine cycle or Rankine cycle. And then the superheated Rankine cycle, reheat Rankine cycle, and regenerative Rankine cycle. So the reheat and the regenerative are optional. Okay, so most important thing is Carnot, Rankine, superheat Rankine. So in vapor Carnot cycles, first we take a look at our TS diagram. Earlier, what we have looked at is the PV diagram. So now we go to TS diagram, but this time is for a Carnot cycle. So you have T, absolute temperature in Kelvin, and entropy in kilojoules per kg K. So this will be the saturation dome. So remember, whenever it refers to vapor or steam, you must always include the saturation dome. For gases, you don't have to. Only for substance which undergoes a change in phase from liquid to vapor. Liquid to vapor. We are to solid. We are looking at liquid to vapor. Okay, so anything that exists as vapor and liquid, okay, we have to include the saturation dome. So on the TS diagram for a vapor Carnot cycle, you have the high temperature and the lower temperature. So from the higher temperature usually is the heat source, and TL is usually the heat sink. So you have two isothermal line, constant temperature line, and two isentropic line. That is the reversible adiabatic. Okay, and at the same time, on the TS diagram, your pressure line should look like this. This is the pressure line, and this is called the boiler pressure, and this is called the condenser pressure. Or you can have high pressure and lower pressure. So for Carnot cycle, it is operating based on two temperature limit and two pressure limit as well. So you have the cycle, the intersection point 1, 2, 3, and 4. So point 1 is saturated liquid here. Point 2 is dry saturated vapor. Point 3 is wet vapor. And point 4 is also wet steam or wet vapor. And then it goes in the clockwise direction. So 1 to 2, state point 1 to 2 here is the isothermal heat addition, heat supply, the boiler. So the device that we use for this process is the boiler, the steam generator. Okay, so you can see there is an increase in entropy. So that is why we say heat supply is here. Then 2 to 3 is where you have your isentropic expansion. So in the turbine, so the device for this process is the turbine, where it undergoes a drop in pressure and temperature from the higher temperature region to the lower temperature region. Okay, so that's a turbine. So from the turbine, work is extracted. So you have work output. From here, you have heat supply. From here, you have work output, work done by the system. And then the work is converted to electrical energy. Then from 3 to 4, as we have mentioned, based on your heat engine cycles, not all heat energy can be converted to useful work. Energy which cannot be converted to useful work will have to be rejected from the system. And we call it as the heat rejected, and the system will undergo a cooling process in a device which we call condenser, where condensation will start to take place. Okay, so it will move from state point 3 to state point 4. But in the Carnot cycle, state point 3 and state point 4 both are in the wet regions. So you must have the dryness fraction. Then 4 to 1, since we need to recycle, okay, the working substance. So what happens is we have to convert the vapor, all the vapor, back into liquid. So that is why point 1 is sitting on the saturated liquid line. So the pump will compress the liquid or water from the low temperature, low pressure region to a higher temperature and higher pressure region. So during these two isentropic process, there will be no heat flow. The only thing you have from 4 to 1 is work done on the system, which we call work input. So, and then since this is a TS diagram, so the area of the TS diagram is equivalent to heat flow. So the area below the process path from state point 1 to 2, this entire surface area, this entire area is considered as heat supply, and this entire area is considered as heat rejected. That will be shown here in this diagram. So this is TH, the higher temperature, source temperature, and then the two isentropic process, constant entropy. This area represents heat supply. This is your state point 1 to 2. Okay, state point 1 to state point 2. So this area is equivalent to heat supply. So you can find this by taking the height multiplied by the base. So that's heat supply. So therefore, heat supply is equals to the height multiplied by the base of 2 minus S1 or S3 minus S4. For heat rejected, now basically you still have to remember that, okay, most of the time we need network out to calculate, okay, the cycle efficiency or the Rankine efficiency later on, or the Carnot efficiency, and etc. etc. Okay, so that is very important for us to know how to obtain the heat supply and the heat rejected based on the TS diagram, based on the TS diagram for heat, based on the PV diagram for work. Okay, so since it is a two-phase substance, so remember, put in your saturation dome, and then this time we are looking at heat rejected, which is at the lower temperature. So that is the lower temperature line from here, and these are the two constant entropy line. Okay, so we are moving from state point 3 to state point 4. Okay, and then this area here should be the heat rejected. Okay, so this area will be equals to the height multiplied by the base given by this. So the thermal efficiency, remember, or Rankine efficiency or Carnot efficiency, or in general they are all called the thermal efficiency, is defined as desired output over required input. So before we can find out the desired output, which is the network out, first thing is we must know the heat supply and the heat rejected. So since thermal efficiency is defined as desired output, that is the network out, okay, over the required input, the energy input is in the form of heat supply. Okay, network out over heat supply. So based on your engine cycles again, Carnot cycle. Okay, so remember energy balance. Based on energy balance, energy received, energy rejected. The total energy received must be equal to the total energy rejected. So that is why you have this equation here. So to work out the desired output or the network output, so you have to take heat supply minus heat rejected by changing the network out to be the subject. So remember, the substance that we use here is water. Okay, water with high heat capacity. So from this, our network out, which is equal to heat supply minus heat rejected, and these are the formulas that we have. What we do is we just substitute into this main formula. So we have this. So and then manipulate, you got this. Then come back to the definition of thermal efficiency. So you have this. And then when you simplify this, you got the thermal efficiency or the Carnot efficiency for a vapor Carnot cycle. For this vapor Carnot cycle. So advantages and limitations of Carnot cycles. Ideal, that is the best, that is the most efficient cycle. Okay, that's Carnot cycle. And what are the limitations? Now, the Carnot cycle is the most efficient cycle operating between two specified temperature limits, but it is not a suitable, I repeat from the beginning, it is not a suitable model for power cycles. Because of what? First, the process 2 to 3. Okay, the turbine cannot handle steam with high moisture content. Okay, so let us go to the TS diagram. So now, state point 2 to 3 is here. Okay, so at point 3 here, okay, we can say at state point 3, the moisture content is very high. The dryness fraction is somewhere around 0.6 from my diagram, 0.6 or 0.7. 0.6 and 0.7 is known as poor quality steam. Poor quality steam. Any steam which has dryness fraction more than 0.9 only is considered as high quality steam. High quality steam, the dryness fraction must be more than 0.9. That means X greater than 0.9. Any X that is less than 0.9 is considered as low quality steam. And this low quality steam will cause the impingement of the turbine blades, okay, and causing erosion and wear to the turbine blades. So this make it not suitable to be a power cycles, because when we use a turbine, and then if this happens very frequent, then the turbine will damage, okay, and then the turbine is a very high cost device. Okay, process 4 to 1. This is a pump. This is where they use a device called pump. Now here the pump involved in two-phase substance, that is liquid and vapor. Now most of the pumps, or we can say all pumps, actually they only operates under single phase. That means it is completely air or it is completely liquid. It cannot operate based on steam, dry steam, and water. So what happens if the pump operating based on water and it is handling two phases? The pump will burn out very, very fast. Okay, so these are the limitations of Carnot cycle, and which make it impossible, not possible, okay, to be a power cycle. And from that, okay, later on, we have the modification of Carnot cycle to something which we call the Rankine cycle. Thank you, everyone, and stay safe.